Hello. I would like to calculate now the length of the circle using Cartesian coordinates. So I have in here my quarter of a circle like this, and I have in here a segment like this, and in here I have the x, this one it's x, and in here I have df. The formula for calculating the length of a function is the following: 1 plus f prime of x squared dx. In our case, a circle centered in origin is x squared plus y squared. It is equal with r squared. So y, it is equal with plus minus r squared minus x squared. The derivative of this function is dx from r squared minus x squared. It is equal with r squared minus x squared, its derivative derived, it's minus 2x. Then I have 1 over 2 from this function, and I have 1 divided by r squared minus x squared, and this is equal with minus x divided by r squared minus x squared. If I calculate the expression, it's radical from 1 plus minus x divided by r squared minus x squared, and this is equal with square root of r squared. This is in here is like this, and this is r squared minus x squared plus x squared over r squared minus x squared, and this is equal with r over square root of r squared minus x squared, like this. Now the next step is to create the integral. It's integral from 0 to r, from r divided by square root of r squared minus x squared dx, and this is equivalent with we have to apply the change of variable, and this is equal with integral from 0 to r, from r divided by r multiplied by 1 minus x over r squared dx. This simplifies, and now we do the following. We change the variable in order to simplify the calculations. I have x over r, it is equal with cosine of alpha, and x, it is equal with r cosine of alpha, and I have dx, it is equal with minus r sinus of alpha d alpha, and alpha it is equal with arc cos x over r. Alpha of 0 it is arc cos, so the arc, the angle which cosine is 0, I have pi over 2. Alpha of r, it is the arc of whose cosine is 1, and this is 0. And then I have in here the following equivalent integral is not equal. Integral from pi over 2 to 0, from 1 over square root of 1 minus cosine squared of alpha of minus r sine of alpha d alpha. I have in here cosine squared of alpha plus sine squared of alpha, it is equal 1, and then I have sine squared of alpha, it is equal with 1 minus cosine squared of alpha. Then I have in here integral from 0 to pi over 2, and I put r in front, 1 over sine of alpha multiplied by sine of alpha d alpha, it is equal with r integral from 0 to pi over 2 d alpha. And what we see, this is exactly the same as the expression of calculating the length of the circle using polar coordinates, with the exception of the limits of the integral. Because as we calculated only a quarter of the circle, this will be equal with r alpha from 0 to pi over 2, it is equal with r multiplied by pi over 2 minus 0, it is equal with pi over 2 multiplied by r. Because I calculated only a quarter of the circle, the final result is 4 multiplied by pi over 2 multiplied by alpha. This is 2, this is 2πr. So in the end, LC it is equal with 2πr. Like this. The most important thing is that when I calculated the integral using Cartesian coordinates, by using the second method of changing variable, by changing x over r with cosinus of alpha, actually what I did was to change the system of coordinates in which my integral is to be calculated, and implicitly to go to a graph of the function that is a little bit simpler to calculate. In the case of the circle, when I went to polar coordinates, the integral, it was extremely simple to calculate. But also because in many courses the second change of variable talks only about replacing expression with trigonometric functions like this. Actually, if you think, it's not absolutely necessary to use only trigonometric functions. The idea is not to use trigonometric functions, it's more like to go from one coordinate system to another, which is in which the integral is simpler to calculate. And there are many other coordinate systems and expressions which make certain integrals simpler to calculate. Thank you for listening.